Hi guys, welcome to another flip lecture on water and solutions.
Water!
Solutions! All right, here we go.
So just some interesting water factoids so that you understand why it's important that we talk about water. You are nearly 70% water.
That's crazy. Where is it found?
In your cells.
Nuts. Your cells are filled with water and surrounded by water. So not on the inside, also on the outside.
That's right, which is very important. We'll talk about that in a second. And lastly, the important part is that it helps to transport substances in and out of those cells, which is highly needed.
Yeah, if transport didn't happen, you would be dead.
Yes.
You would die.
Dead.
You would be dead.
Doornail.
Life would be hard.
Yep.
Because you would be dead.
Yep.
All right, so let's talk about the first characteristic of water that people tend to have a hard time with, this concept of storage of heat or high specific heat. What does that mean?
So it basically means that water acts kind of like a bank, and it can absorb a whole lot of thermal energy before it changes a degree in temperature. And in layman's terms, that means that it heats up and cools down very slowly in comparison to a lot of other substances.
And in layman's terms, it explains why water takes forever to boil.
That's right. Watch pot never boils.
Never.
But that means that it's very important and good that you are made 70% of water, because that means that you can absorb a lot of that heat without changing a degree in temperature. That reminds me of a word.
Homeostasis.
Homeostasis. Yes.
Yes, nice. So we can actually use water to maintain homeostasis, and we use it by doing something called sweating. But oftentimes sweating in a science classroom, we don't call it sweating. That's kind of like the term you would use like on the playground, at the lunch table.
In gym class.
When you're not cool. All the cool kids call it
evaporative cooling.
Also known as perspiration.
Very good. All right, so this guy here is doing some work. And whenever you're doing work, your muscles are working. And when your muscles are working, they're doing a lot of chemical reactions that are producing heat as a byproduct. And so whenever you're doing a lot of work, you're producing a lot of heat. And if you're producing a lot of heat, if you didn't have some way of getting rid of that heat, there'd be no way for you to maintain
homeostasis.
That's right. So this guy, if we were to look very closely, probably has some beads of perspiration on his upper lip. Mm-hmm. He might have some perspiration in this
the pits,
axillary area. Mm-hmm. Yes, because the way your body reacts is it gets all these sensory information from your environment to say, whoa, I'm overheating. I'm leaving homeostasis here. I'm leaving my set point. And then your body kicks in on a lot of different levels to bring it back to that 98.6. And in this case, by perspiring and losing some of that heat that's stored in that water.
So what's actually happening is, if we look at it on the physiological level, heat from the body is being moved into or stored in water, and that water, via the sweat glands, are being moved to the surface of the skin. And the great thing about water is it can hold all of this heat and not damage the surface of your skin, because it takes a lot of heat in order to raise the temperature of water, even 1 singular degree. So when that water evaporates off the surface of your skin, not only is the water leaving, it's also taking with it
the heat.
There you go.
Nice.
It also explains why if you are wet and you sit in front of a fan, you get very cold.
Hey, how much you want to bet that I would win if you and I had this machine in our classrooms?
I would bet you all of my students' ears that you would lose.
Done. Challenge accepted.
Okay. Oh, no.
All right, so let's talk about the chemical formula of water. So water is 1 oxygen atom joined to 2 atoms of
hydrogen.
Kind of looks like Mickey Mouse, no?
Yeah, and if you look at it, you notice there's actually a huge difference in size, which is important.
Yes, that is very important. Go on, because it shows the picture.
So here's what we're talking about. We have our 1 central atom of oxygen and our 2 Mickey Mouse ears of hydrogen sitting on the 2 opposite ends. You'll also notice that there's this weird color change here, and there are these lines connecting the hydrogens to the oxygen. So let's talk a little bit about that, because it'll bring in some of the information that we talked about in our last lecture.
That's right. So oxygen is what we call electronegative, and that means that he really likes to be negative. And the reason that he likes to be negative is because he's larger. And what he's trying to do is to fill that outer valence shell, because for any atom to be chemically happy and stable, it needs a full outer shell of electrons. And oxygen by himself only has 6 electrons, and to be full, he would need
8.
Right.
So that's why he has his 2 friends here. We have 2 hydrogens, and they're in this precarious situation too because they also want to have a full valence electron shell. But what do we know about them?
They only have 1 electron.
And in order to be stable,
they would need 2 in that outermost level.
So what would make sense then if we have 2 hydrogens that each have 1 electron, but they need 1 additional one to be stable, and we have an oxygen that only has 6 electrons and is looking for 2 more to gain?
I say partnership.
Sounds good.
Yes. So if oxygen partners with these hydrogens, then if they all share the electrons, sometimes oxygen would have 8. Right? Sometimes hydrogen would have 2, and the other hydrogen would have 2. But can they share them all the same amount of time?
No, and if you look, you notice that one side of this water molecule is green, and the other side is purpley pink. And if you look at this little structure on the upper left-hand corner, you'll notice that that color applies to a charge. And so if we think back to what we talked about previously, we know electrons have a charge. And what is it?
Negative.
All right, so that means whatever atom is stronger, can pull the electron closer to it, is going to take on more of the charge that that electron has.
All right, I see.
So can we tell by this color that one structure or one atom is actually stronger than the other 2?
Oh, absolutely.
All right, let's talk about that.
So water, if we remember from our last lecture, is held together by covalent bonds. And the co means sharing. And that means that these particular electrons, or these particular atoms, are sharing their electrons. They're sharing something tangible, some actual thing. And that means that these are really strong bonds. But we did say that the oxygen was a lot larger. So would we say that he's probably going to be an equal sharer?
No, large people tend to want more than their fair share.
I have that, yes. They tend to bogart things. Yeah. So oxygen, if he's larger and more electronegative, he's going to hold on to those electrons for longer. And if he holds on to those electrons for longer, that means that he is going to develop what?
A negative charge.
A slight negative charge, because he's not going to have equal numbers of protons and electrons anymore. He still has 6 protons, but now he's gotten these other 2 electrons from the hydrogens that he's also holding for a certain amount of time. So he becomes slightly negative.
And the opposite is going to be true for our hydrogens because they're going to have the electrons less of the time, and they're not going to be sitting as close to them as they are to our oxygen. So that means that they're going to have a slightly more positive charge.
Right. And would we say this is a definite negative and positive charge?
No.
No. We would say that it's a slight.
Yes.
Okay.
And we would also say that there is an opposite, there are differences on opposite sides of this molecule in terms of charge. That's important.
Okay. So those opposite ends that you were just talking about, we end up calling poles, right?
Just like our planet.
Exactly. And so one end of a water molecule ends up having a negative pole, and the other end ends up having a positive. Okay?
And that's really important because that difference in charge helps to explain a lot of the interesting behaviors that water has that no other substances on our planet have.
So we could say that every special property of water comes back to this idea of polarity.
I think we should say that, and I think in the future maybe those people watching this should say that if they happen to see it on a quiz. Hint, hint.
Got it. So what analogy could you give me if I was still struggling with this idea of oxygen being electronegative and the hydrogens being a little weaker and oxygen bogarting?
So my favorite analogy is visualizing a sumo wrestler.
I might need a visual.
And a skinny little boy.
Could you give me a visual maybe on that?
This is what I'm talking about.
That really, I see it now. That really brings it in.
So let's go ahead and label our sumo wrestler. So our sumo wrestler is super large, right?
Okay.
So this guy has to be the what?
He's going to be oxygen. He's going to be the electronegative oxygen.
Okay. And then we have this skinny little boy, and although there's only one, it would be more accurate if we found 2, but it's hard to pay skinny little boys to do this in public.
True.
Okay, so we only have the one hydrogen. But the way in which they are interacting with one another is very similar to the way that the oxygen in a water molecule interacts with a hydrogen. They're fighting for something.
They are fighting for the electrons.
That's right. And even though technically they're sharing, they're not sharing equally, and that's the key.
So if I wanted to put my charges here, I would put a negative charge by the sumo wrestler, and I would put a positive charge down here by my pretend two boys here, my two hydrogens.
And another example, if this helps you visually, is to think about tug of war. So in tug of war, we have two teams. They're on opposite ends of the rope, and technically they're sharing the rope.
Right, technically.
But what is the goal of the game?
Well, the goal is to get more of the rope onto your side. Hold it for longer on your side.
So if oxygen and hydrogen were playing tug of war, they'd be sharing the rope, but
oxygen, which would be me in this scenario, would pull the rope entirely to its side. Yeah, look, I bring the pain. Everybody knows it.
That's clearly my uncle.
Okay, we'll just have to do it for reals.
All right, so let's talk about polarity a little bit more. And the reason why we're spending a lot of time on this concept is because, hint, hint, wink, wink, this is a big deal on the quiz and also on the test. This is as big a deal as the whole homeostasis metabolism question.
Absolutely.
And this question tends to be, for some reason, something that people miss every single year. So let's really drive it home, Creasy.
I think we should drive it home.
All right, so oxygen is stronger than hydrogen. And that is a truth.
And let's use a clinical word here, a biological word. Stronger, yeah, that's okay.
More electronegative
is better.
So it is hungrier or has a stronger pull
on electrons.
On electrons. And electrons have what charge?
Negative.
So whatever the electrons it's closer to, for most of the time, will take on a similar charge to itself.
Yes. And why is that again? Why, if I hold on to electrons, do I suddenly become more negative?
Because I would take on the charge of the electron. I'm adding it to me, so my electrons and my protons are no longer in balance.
Okay. So no more balance on electrons and protons. We've become imbalanced now. All right. I think I get it.
You got it?
I got it.
You could also think about the Earth.
Poles.
You could also think about a magnet.
Poles.
You could also just think about water.
Poles.
Poles. So here's another example. This was not filmed at my house.
Nor mine.
All right, so we have, let's call him Sid.
Sid?
So we have Sid over here. Sid is in a struggle right now for a dog toy. And here's a dog. We'll call him Bob.
Bob.
So we have Bob and Sid. So Bob and Sid, technically right now, they're sharing this toy.
Which would be the electrons.
Right.
That are needed to fill a valence shell.
Right. Now, although Sid is larger in size, we know just, anecdotally that when we think about a human jaw versus a dog jaw, which one is going to be stronger?
Heads up. Hands down. Sid. I mean Bob. Bob.
You don't even
Bob
know
Shaw.
Your dog's name.
Bob's jaw. Bob's jaw stronger.
You don't even know your dog's name.
I'm a bad dog parent.
Anyways, so technically they're sharing it, but if we let them start to really go at it, like if we were letting them go at it in tug of war, even though they're sharing it, we know that Bob would be able to physically move that toy into, so that it's not being shared equally, so it'd be more in his possession than it would be in Sid's.
Oh, absolutely. Sid's going down.
And if that dog toy had a negative charge because it represents an electron, what does that mean about Bob?
That means that suddenly Bob becomes slightly negative.
And what happens to Sid?
Sid becomes slightly positive.
But does Sid truly have a positive charge?
No, it's only a slight, subtle charge. Because he's still holding on to an electron for a little bit of the time. Just not as much as he would be without Bob being present.
Oh, Bob.
Oh, Bob.
He's a cutie.
Have you ever noticed how your mouth opens back up when you say Bob?
Let's move on. All right, so here is that same picture again. Why do we keep showing them the same thing over and over?
Really, Cook, I believe it's because they'll see it again and again and again.
And again and again. So let's talk about it quickly. What is this a structure or a picture of?
This is a water molecule, H2, because we have two of them, O for oxygen.
And we know that they are bonded together, but how are they bonded together? Is it ionic?
Well, they're sharing, so it's got to be covalent.
Excellent. And we know that they're going to be sharing electrons, but are they sharing truly? equally.
No, they are not sharing equally. Oxygen is bogarting the electrons. He's holding on to them for longer. He needs that 8 because he only has 6 currently. So he holds them for longer, becoming slightly negative.
And the hydrogens?
Slightly positive.
So it's as if they're playing tug of war with the electron, and who is winning the game?
I believe oxygen.
And oxygen represents me in life.
Wrong. Me. So, let's go back to other unique properties of water. So we talked about water having a high specific heat, and now that we know about polarity, let's take a moment and explain why water has a high significant heat in relation to polarity.
Because it takes a lot of energy to break those bonds.
So water molecules have all these bonds between them because of these slight charges that they have, and that means that they're all kind of connected in some way to one another. And so for me to break them, I would need a lot of energy.
You would need a lot of energy. So it's able to hold that extra heat, theoretically, in its bonds, and it can hold a lot of it before that bond has to release or break.
Okay, I get it.
All right, so the next major term that we're going to talk about is something called cohesion.
Again, that prefix of co.
Yes. So cohesion is this interesting phenomenon. You guys have probably seen this before, where water likes to stick to itself.
I have definitely seen this before.
How is it possible for water to stick to itself? Does water have a charge?
Well, yes, kind of. It has a slight charge.
Because it's
polar.
So are you telling me that if I have one water molecule and its oxygen is kind of hanging out over here, and I had another water molecule and its hydrogen was hanging out over here, that because they had a slight difference in charge, that there'd be an attraction between the two?
Well, what do opposites do?
Attract.
That's right.
Just like true love.
That's right.
Oh, that's nice. All right, we're over it.
Okay, so we have this end of a water molecule, which is negative, slightly attracting this end of a water molecule, which is positive. And we have this weak, but still there, force of attraction that's holding these two together.
And this weak force of attraction that we're talking about has a name.
We've talked about this already. And that weak force of attraction between two polar molecules here is what we know as a hydrogen bond.
Which is the weakest of all the bonds.
That's right. Does it only form between hydrogen?
No.
No. Anything that bogarts electrons can form a hydrogen bond, right?
Yeah, that's true.
So not just oxygen and hydrogen.
So cohesion, think about co-pilots, right?
Co-pilots.
Co-pilots do the same thing, so it's water sticking to itself.
Right.
Really important.
And when we talk about cohesion, one thing that we can specifically talk about is surface tension. So if you've ever filled a glass way, way, way above the brim and it hangs there before it falls over the edge, the reason it's able to hang there and kind of defy gravity for a little bit is because of all those bonds in that water holding all those molecules together. It has to get pretty high before gravity can actually disrupt those bonds.
Yeah, and it also explains why things like water striders can actually walk across water without falling through the surface.
Yes.
So when we talk about this tension, that tension is generated by hydrogen bonds.
Okay. And I think we have a picture here of a hydrogen bond, so we're looking at how these things are connected by our different poles. So we look here, we have our negative oxygen connecting to or attracting our slight positive of the hydrogen end. And we can actually have many water molecules sticking together through this.
Yeah, it's pretty cool.
It is pretty cool. And then, like we said, water striders. So what property?
Surface tension.
Surface tension.
And
cohesion. And it all goes back to, what can we go back to?
polarity.
Polarity.
Man, that would be an in-depth question.
That would be. Hint, hint.
Love it.
All right, so another unique property of water is water's ability to stick to other things besides just itself.
And this is sometimes an annoyance.
Yeah, so really anything that has a charge might start to attract a water molecule because water also has regions of charge. So things that have charge like glass, water could perhaps stick to.
It's the reason why dishes take so long to dry.
Yeah, exactly.
How about hair?
Hair?
Oh,
yeah.
Hair takes forever
so much charge.
to dry.
And if you have curly hair, you got all the sulfur bonds.
Boy, man.
It's such a pain. But yeah, that's why. Water can climb up a paper towel. for the same reason. It's clinging to regions of charge and that cellulose of that paper towel. And what we call basically water moving up a tube is called a capillary action, because we call those thin glass tubes capillary tubes. If you've ever had your finger pricked and they put that tube on it and the blood moves up that tube, blood has water-based.
That's pretty morbid. Let's go with something that everybody knows.
Okay,
let's talk about
fine.
straws. Right? Straws in a glass.
Okay.
Have you guys ever noticed that when you put a straw in a glass, and bear with me here, some of you might know this, that if you go to McDonald's, the diameter of the straw is pretty big. But if you go to some other fast food restaurants, the diameter gets smaller and smaller and smaller. So this is a fun little experiment. The next time you get a chance, go and collect straws from different eating establishments. Bring them home, open them up, and put them into water or put them into whatever you happen to be drinking. And you'll notice that the smaller, the skinnier the diameter of the tube, the farther up the liquid will travel.
Oh, why is that?
Capillary action.
Oh, nice. Let's relate this to something in nature that's not morbid. Trees.
Oh, trees.
Trees are a great thing to relate this to. So
trees
are very tall. They have to move water around.
Water comes from the bottom, from the root system.
It's got to move towards the leaves. So if we were to create a structure in order to move water upwards without having to have a pump or some kind of mechanical mechanism, what kind of structure might I use?
We would need some sort of tube, and we'd have to pay very close attention to the diameter of the tube.
Exactly. So trees actually have structures that look a lot like straws that are narrow in diameter, and they use those structures in order to help water move up, a leaf or up a plant stem. And so if a drop of water leaves by transpiration,
evaporation off of plants,
and you need to know that because that's in your study guide. So if one drop of water leaves by transpiration, it basically creates a tug on the drop of water behind it.
Why?
Because they're connected.
And what is it called when water sticks to water?
Cohesion.
So we have cohesion happening here, but we also know that water is actually sticking to the walls of this tube, and that's not water, so what is that called?
That must be the adhesion.
So we're talking about two different terms that apply to water's attractiveness to either itself or to other things that are responsible for transpiration.
Yes, and we could also work in the capillary action term here, because that's basically what's happening in a plant, is that we have this capillary action through these plant straw structures.
That's deep. You took it there.
I did. You need to know that, though. Hint, hint.
I also took it there. So here's what we're talking about. If you look at this particular, we have different diameters of tubes. You'll notice that the skinniest diameter tubing has the movement of fluid going farther up. And then the largest diameter tube, even though we have some movement, it's not as significant. So if you had to design a tree or design a plant or design some sort of piping system to move water against gravity and you wanted to do it in an energy efficient way, here are some great scientific principles to apply.
Smaller is better in this case.
Smaller is better.
Yes.
Smaller is better. All right, so let's apply it to this picture. We have a spider web, and we have water droplets that appear to be stuck on the spider's web. So which chemical property allows water to stick to the spider's web?
I'm really going to have to go here with adhesion.
That's right, because we're adding water to something else.
Nice.
Adhesion.
Nice.
Can't be cohesion.
Nope. It's water sticking to a different substance here.
Why can't it be capillary action?
I don't have any glass tubes or tubes of any kind.
All right, let's move on. All right, polarity again. That important, huh?
It's that important.
All right, so the polarity of water enables lots of substances to be dissolved inside of it. Water is known as a
universal solvent.
Write it down, that's really important. So water is a universal solvent, but there's a reason why so many things can dissolve themselves into water. And if you ever get confused about the word solvent or solute, the smaller word fits into the
bigger.
Yeah, pretty simple. So let's talk about an example. Kool-Aid. Delicious.
Kool-Aid is delicious, and Kool-Aid is made up of lots of sugar molecules.
And sugar has?
And sugar has regions of charge, because it has a bunch of different groups that hang off of it. And those regions of charge start to attract what?
Water.
Water's regions of charge. And so basically what happens is we have these water droplets that will start to surround our molecules of drink mix and start to pull them apart, which is what creates that dissolving principle.
Yeah, so they physically can't get to the other molecules that are like themselves.
Exactly.
And so here's the thing, though. What if something doesn't have a charge?
Well, since opposites are attracting, you would have to have an opposite to attract to. And if there wasn't an opposite, I imagine you wouldn't be attracted to it.
So give me an example.
Nothing to stick on to.
Give me an example.
So if I put, let's say, olive oil in a pot of water, what I see when I add that olive oil is a bunch of olive oil discs or circles or blobs on the surface of the water. I don't really see a mixing or a dissolving happening there.
So let's talk about what's actually happening here, because if something has a charge, water has this goal. It's to separate them out so they can't touch one another. But it doesn't know what to do with oils or non-polar substances, things that don't have a charge. Doesn't know what to do with those things. So instead of trying to break them up, it just wants to contain them. It's herding them into these pockets.
It's like a border collie.
It's exactly like a border collie herding sheep.
That's right.
So oil is the sheep.
Mm-hmm.
Water is the
border collie.
Not as cute as a border collie.
That's true. That's true. But this is a very important principle because the reason that you're not dissolving when you go swimming is probably because why?
Because you're covered in
oils.
That's right.
Everything in your body that doesn't want to dissolve or can't dissolve for any particular reason is going to be coated in a layer of an oil.
Oil's your friend.
Otherwise known as a lipid, which we'll talk more about later.
Oh, that's going to change your life.
It really
when we get to it. It's going to be amazing.
So, universal solvent is a big principle. And that's really important because your blood has a lot of, what do we say? Water. And so things that need to move through your body often are dissolved in your blood, which is aqueous, is composed of water, so that it can be transported throughout your body.
So I can take this Kool-Aid from 1982 and pour it into this water, and I'm going to get the, Kool-Aid man.
Right.
I'm going to get him because water is taking each one of those little particles or little molecules of Kool-Aid and separating them out so they can't get to one another.
Exactly.
And that's why they're so delicious.
So delicious.
So delicious. All right, so here's another example. In this time, we're going to start with something that's non-polar, doesn't have a charge.
Right. So we have a big bottle of lipid or olive oil or vegetable oil.
Okay, and we're going to pour it into our water, which is still our universal solvent.
Right, but here we don't have anything for water to start sticking to. So it acts like a border collie and starts to herd those lipids together, and so these lipids start to spontaneously form spheres or circles.
Which also explains how lava lamps work.
Ah.
Lava lamps.
I love that. That also from 1982.
Or a little bit earlier.
Maybe a little early.
I wish I had a lava lamp.
Yeah.
I did have one.
You did.
Let's move on.
So, another important component of water here that we need to talk about are acids and bases. So basically, when we have H2O, a molecule H2O, that H2O can be split apart.
Yep.
And if we split H2O apart, what would we be left with? Because let's remember here that oxygen is really, really electronegative.
Yeah. So what you're going to end up with is something called a hydrogen ion. So one guy's just going to be left out to hang out on its own, which is going to have a positive charge. And then because it's missing an electron, it's not happy. But this oxygen is so strong that it's able to hold on to one of them. So you're going to have a hydroxide on the other side, which is going to have a negative charge.
And let's refresh again. So why do I call these things ions?
Because they have a charge.
Ah, okay. And they have a charge because they have different numbers of protons and electrons.
Yes, so the protons and electrons are not balanced. So let's talk about what determines whether or not something's an acid or a base. So that means that we have to talk about something or a scale that we call the pH scale. And the pH scale is actually designed to measure the concentration of something very specific in solution.
So maybe we can remember it by its
power of
hydrogen.
Oh, you are so smart. Wait, I came up with that. I'm so smart. So our power of hydrogen. So our pH scale is actually measuring how much hydrogen or how many hydrogen ions are present. And the weird thing is that it's counterintuitive because the more hydrogen ions you have,
the lower you are on the pH scale.
Because it's based on a logarithmic interaction. So, but we're not going to talk about that. That's too much for our class. But what we do want you to know is that the less hydrogen atoms you have, the more
hydroxide ions.
So that means that you would become more
basic.
And we're moving further up the pH scale. So let's show you what that actually looks like.
So pH scale goes from 0 all the way up to 14. And remember we said that the higher the hydrogen concentration, the lower we are on the pH scale. So first we have to find what our middle is, and that would be what?
7.
Okay, so 7 is neither an acid nor a base. So what
we
would call
refer it as neutral.
Neutral. And so anything that has a lot of hydrogen and therefore is lower on the pH scale is going to be an acid.
Mm-hmm.
So anything that is below 7 is an acid, and that means that anything above 7, which is going to have more OH or hydroxyl ions, is going to be a base.
Also known as an alkaline.
Yes.
Okay. All right, so let's actually visualize what this looks like now.
So some interesting things. So right at neutral, pretty much the only thing that we're going to see in biological systems is going to be pure water.
Pure water.
Distilled water.
So if we were to ask you roughly what do you think your body fluids are in terms of the pH scale, you would say they should be right around 7.
Yeah.
They sit a little bit higher than 7.
Yeah, blood is slightly alkaline. It has like 7.14-ish, but it's pretty neutral.
Yeah. The only time that we're not going to be talking about neutral solutions in the body is when we're talking about our digestive system, clearly because we want to break down food product.
Right, exactly. And the more acid your stomach, the better breaking down capabilities you have.
Yeah, so let's talk about the acidic side of the pH scale first.
So acidic. So when you eat acidic things, they make you want to pucker. They're very puckering. So things like citrus and tomatoes and vinegar. If you've ever had something like a cut on your lip and you have eaten something citrus, then you have experienced some acid on your lips.
Pain.
Yeah, lots of pain.
All right, let's talk about the other side.
The other side, we have our bases, and some of our stronger bases we use in cleaning. So soaps.
That's key.
Yeah.
Cleaning products tend to be basic.
Ammonia, bleach, soap, drain cleaners, oven cleaners, they're all going to be strong alkalines.
Yeah. So if you guys have ever seen a shampoo commercial, right on the bottom, they're like, oh, it's pH balance. They don't know what they're talking about. There's no such thing as pH balance. Another example of society using science.
Bad science.
In a bad way to trick
society.
people. Because if shampoo is a cleaner.
It's not going to be working on to clean your hair if it's 7.
7, you bought water.
Yeah.
Nobody wants to buy water unless they want to buy water.
Greasy heads.
I don't know.
All right, so we're going to just sum up what we just covered so that we have a good understanding of what you just learned, what we covered. So first, I think best thing we could say is the idea of polarity. That water is a polar molecule, and because water is polar, all the unique properties get traced back to the fact that water has these poles.
So what are those unique properties?
Well, we said that water has a high specific heat.
Okay,
so high specific heat. We talked about... And we said that it has that high specific heat because of those bonds between water molecules.
So and those bonds are hydrogen bonding. Yep. So hydrogen bonding is possible because of polarity.
Right.
But the other types are the other two ways in which water bonds to either itself or to other things is also due to that polarity. So we're talking about cohesion, when water sticks to itself. Co-pilots doing the same thing. And adhesion, when we're adding water to something else, to glass, to hair, to the surface of your skin, so on and so forth.
And then the last thing we talked about is that water is a great solvent. Because it has those regions of charge, it can attract lots of different things and either herd them into spheres if they're nonpolar, or break them apart and dissolve them if they are also polar molecules or have regions of charge.
Right. So if we gave you an unknown substance and we told you to add it to water and to come up with qualitative data about the interaction, you should be able to, based on that qualitative data that you've collected, determine whether or not that unknown substance is polar or nonpolar.
That's right. And then the last thing we talked about was the pH scale, that we are measuring the power of hydrogen. And that we said things that were higher in hydrogen are actually lower on the pH scale and are acids, so anything below 7. And anything that is higher than 7 has more OH, hydroxide ion, and it is more alkaline, more of a base.
And things that tend to be basic are cleaners in general, and things that tend to be acidic are things that make you, as Creasy said, pucker. Body fluids tend to be?
Right around 7, right around neutral.
Because we're mostly made up of
water.
And that's the first thing that we talked about.
That's right.
And don't forget, polarity is a big topic, so think about the analogies that we talked about in the lecture.
I'm going to draw some what I consider important hatch marks around polarity.
No, you should draw lightning bolts.
Um,
No, I meant stars.
okay.
No, I meant a Fraggle.
Oh.
No, I meant a smiley face. Oh, good. You anticipated my needs.
I did.
Good luck, guys.